Good afternoon, colleagues. This is the T1 S1 session, Water Scarcity, Space Technologies to Monitor Precipitation, Soil Moisture, and Drought. I'm Jorge Gutierrez from FAO in Colombia, and it's my pleasure to present Mr. Freddy Angel Soria. Mr. Soria is a civil and environment engineer with interest in environment health, water, sanitation, and remote sensing technologies. In support to that, he currently works at the Universidad Católica in Bolivia. The name of the presentation is Water Stress from the Andes to the Amazon using SPEI, Global Drought Index data, and ecosystem space-borne thermal radiometer. Thank you so much and welcome.
Thank you so much. I'm very happy to be here, very happy to have such a beautiful audience and in such a beautiful country. And as my colleague said, my name is Freddy Soria. I will present a short work on observations related to water stress using some drought index, SPEI, and water use efficiency index also. Not away. Oh, thanks. Well, during stressful situations, usually the responses of plants is to try to close the stomata in order not to lose too much water because of that situation. But there is also a cost in terms of carbon uptake by photosynthesis. So the questions I will try to respond, perhaps not in full, but at least I will try to wake your motivation or your curiosity. It will be first how plants will respond to a change in climate with changes in temperature, precipitation, and mainly carbon dioxide, CO2, and how will plants respond when extremes such as droughts will hit them. That's what I will talk about today. So into that topic, I will try to guide you through a journey that goes from the Andes at about 4,000 and a little bit more meters above sea level. And we will go down up to the Amazon basin at about 300 to 200 meters above sea level. So I will try to show you how would plants respond with varied geography with observations from satellite platforms. So there's one concept I will use during my presentation. The concept is named water use efficiency. It has been presented briefly by Nina in a previous talk. And the concept I will focus on will be not exactly on the ecosystem water use efficiency, which relates the ratio of carbon assimilation to water evapotranspiration of an ecosystem, but I will focus on plant water use efficiency, which is the total biomass produced by unit of water consumed, or in other words, the ratio of grams of carbon that plants take in 2 kilograms of water that plants release. Grams of carbon per kilograms of water. Well, in a climate change context, the issue is that when levels of CO2 rise in the atmosphere, plants try to adjust to that, as I said, by using the less water as possible while also taking up CO2 during photosynthesis, as I said. But one of the issues that arise from that is that due to global warming, plants tend not to use much water. Plants try to, of course, take up as much as carbon as possible, but it has some limitations. So that's one of the issues I will try to cover today. The importance from a practical perspective, well, there are several aspects that we could evaluate, but I will try to focus, at least in these few minutes, on what would happen when we try to solve or we try to overcome these issues through nature-based solutions in order to promote carbon sinks, of course, to take up those emissions that we generate through our activities, and that's me. So the methods are pretty simple. I have used a standardized precipitation evapotranspiration index, the SPEI, which is a widely known index. I have used also water use efficiency data from the ecosystem spaceborne thermal radiometer experiment on the space station, EcoStress. And I have tried to analyze that data using not so complex algorithms. In this case, I have used unsupervised machine learning techniques from the k-means and hierarchical clustering perspective. On the results part, I want to show you only two parts of what I have observed using those platforms. First, on the upper part are the results from the observations made on the semi-arid areas of the country. As I said, from 3,800 meters to 4,000 meters above sea level, where the vegetation is characterized by herbaceous and sparse shrubs, and droughts that hit that region are from moderate to severe with different durations. As you can see in the graph above, the SPEI has different scales comparing the one in the upper part in the highlands to the semi-tropical lowlands. As smaller the number, then the droughts will be more bad. And in the case of the lower figure, it shows how the droughts will hit a semi-tropical lowland. In this case, of course, droughts will be from severe to moderate in both cases, but the duration will be different. But what about the water use efficiency? In both cases are quite sparse, quite diverse. In the case of the highlands, it can reach up to 1 gram of carbon per kilogram of water. But in the case of the semi-tropical lowlands, as you can see in the y-axis in both figures, it can reach values higher, from 0 to 2 grams per carbon per kilogram of water. What means that? That, for example, when that kind of areas in the lowlands are affected by deforestation or any kind of activities caused by the man, then the effects or the impacts will be higher in terms of carbon uptake, for example, among others. So what happens between the associations between water use efficiency, which is the index I've been showing to you in the previous slides, and the occurrence of, for example, extreme events such as droughts? As you can see, there is no linear relationship. The relationship that we have found in the Latin American area, which I'm showing in the figure below, couldn't be repeated in other parts of the world. In some areas, you could find negative relationships between the water use efficiency index and the drought indices in dry areas. In other regions of the world, you can find some positive relationships, or in some other areas, you can find, for example, in zones with high humidity, positive and at the same time negative relationships. So there's no direct or linear relationship between both kind of indexes. As I showed you before, in Bolivia, the associations are also quite mixed, where you can find water use efficiency, for example, in the low semi-tropical areas from 0, similar to the ones you find in the upper part, in the semi-arid zone of the country, up to 2.5, and that's the difference. You can find in the low part vegetated areas which might be better in terms of trying to tackle the effects of climate change or trying to uptake carbon sources, as it should have been expected because of the density of the vegetation and others. From other perspective, when vapor pressure deficit, for example, increase in case of hotter or even drier conditions, that could stress plants and causes them to consume more water, lowering their water use efficiency, which in this work has been translated as a tendency of plants in those semi-tropical areas which can produce more biomass and can consume less water. We having their water use efficiency that can be as low as in other parts where the vegetation is quite sparse, similar to desert areas. But it can also reach higher values up to 2.5 grams of carbon per kilogram of water. Well, the figure shouldn't look like that, but no problem. In the conclusive part of this short talk, plants can accomplish higher efficiency in lower and humid regions, up to 2.5 grams of carbon per kilogram of water, but the land cover characteristics can also reduce water use efficiency variability. In other terms, there is no linear relationship between both. As I show you, when geographic elevation increases, water use efficiency decreases up to 1 gram of carbon per kilogram of water, but vegetation type can also influence to make water use efficiency even lower. It has been shown also some positive relationships with droughts at short time scales, which are more likely to be observed. Short time scales translated in the indices I've been using. It's from SPI from 1 to 3. 1 to 3, it's related to months, 1 month to 2 months, 3 months, which are more evident in semi-arid climates because plants seem to respond faster to water stress. On the outlook part, it has some practical implications. For example, if we focus on nature-based solutions, those kind of ideas in order to overcome the issues of climate change and carbon uptake could have different efficiencies depending on the kind of plants, on the kind of vegetation, and on the kind of geographical environment that we use that. At the sites evaluated in Bolivia, such is supported by a wide range found at all locations and the wide variability according to seasons. Among the conclusions, to finish this short talk, future applications should evaluate vegetation types, for example, individually, not to focus on trying to reforest areas only with single species, but also it has to be evaluated the seasonal and interannual variability of this kind of solutions. So that would be all. Thank you very much for your kind support.
Thank you so much, Mr. Soria. If the auditory have some questions, please, we can to do 1 or 2, if you like.
Thank you for the talk. Quite interesting. I have just one quick one that was like when you were showing the SPIs in one of the slides, if there was a threshold that you can say, okay, from here to here, you can have certain conditions, or to say the severity that you were showing in some of the graphics, just to see, okay, from this point, going back to the lower values, as you were saying, that they were like worse than the other ones. If you can say there is a threshold where there is like actions that we need to take or something like that regarding the SPI's values, for instance. Thank you.
Thanks. If we are talking about thresholds, which is what I understood from your kind question, well, I think it will depend on the region, and it will depend on the kind of land cover we will find in the region and on the geographical conditions as well as on the climatic conditions we will find in that part. I didn't analyze the aspect of thresholds at this time, but I could consider that for future analysis. And thank you for the interesting question.
Thank you so much. One more? Okay, was interesting to understand the use of the Custris model and the result with the, for example, vapor pressure deficit, no? One small question about that you shared with us, maybe some ideas for share about why plants in semi-tropical, you say, areas produce more biomass and can consume less water.
Um, there might be some reasons. According to the original paper, for example, it would depend on the type of vegetation. The vegetation that in Espanol would be deciduous, I don't know in English, the kind of vegetation which is taller and which lasts along the seasons is the one that can take up higher values of water use efficiency compared compared to, for example, small shrubs and that kind of vegetation that you can find in the case of Bolivia in the Andean areas. That kind of vegetation then in the tropical areas were likely to be more resistant to drought conditions. That's what the original paper said about. And that's very interesting from my perspective for practical applications.
Thank you so much.
Thank you.
Okay. Thank you so much. Maybe the next one, colleague. Is the colleague Rabia Sama. We have the online participation.
Hello, everyone. I am very honored and very pleased to be presenting within the 6th United Nations Conference on Space Technology for Water Management, taking place in Costa Rica from the 7th to the 10th of May of 2024. I am Rabia Samah Shukri. I am PhD candidate at the University of Oran to Algeria, and I will be presenting today my work titled Assessment and Monitoring of Soil Moisture and Drought Conditions in the Orani region, Algeria. I would have preferred to be physically present amongst you today, but due to personal circumstances, I couldn't make it. But I am still very, very grateful to the opportunity granted for me to present my work nonetheless. So my work is structured around 7 main axes. I will start by introducing briefly the research work, and then I will move to the research questions and the objective of the study. Then I will lay the foundation for the conceptual framework by quickly defining some concepts. Then I will introduce the study area and the methodology. Then I will move to the results section and finally to the conclusion. So the drought evaluation and monitoring are essential for determining the impact on agricultural land use, and on food production. In the recent 2 decades, the studies and the research around drought evaluation has increased due to the climate change that has been increasingly noticeable, and it is expected that the climate change, it is expected that it will worsen the drought's impact on agricultural land and thereby limiting crop diversity and lowering the productivity of this land. So one of the ways to evaluate and assess the drought conditions is the soil moisture study. So the soil moisture is a key variable in monitoring and even in predicting meteorological and hydrological droughts, as well as assessing crop and drought events. Advancements in Earth observation, in machine learning, and remote sensing has demonstrated that it is feasible and it can be effective to assess and to measure the soil moisture content across the entire electromagnetic spectrum. And for this, several methodologies have been developed to support this endeavor. The main questions of this study are: how did the surface soil moisture values change from 2015 to 2022? And did the region witness a risk of drought? So the objective of this study is to define the surface soil moisture within the period from 2015 to 2022 using machine learning and Earth observation tools. The choice of method was based on the availability of data, the accessibility to this data, and it has also as an aim to assess the effectiveness of these tools in agricultural land and food security as a consequence, and on natural resources. So as a conceptual framework, we can see through the chart here that climate variations and drought events are interconnected. So the meteorological, agricultural, and hydrological and socioeconomic droughts are linked to the precipitation and to the temperature affected by human activity. The soil moisture is defined as the amount of water held within the soil particles and pore spaces, which is critical for plant growth, agricultural productivity, and hydrological process. So what is the significance of soil moisture in agriculture? Soil moisture is crucial for monitoring agricultural operation, forecasting natural risks, and managing water resources. So this data can anticipate further coming floods or water shortcomings or ahead of time, amongst other indicators. So what does soil moisture influence? Soil moisture influences air content, salinity levels, the presence of harmful substances, soil structure and depth, ground temperature, and heat capacity. Surface soil moisture, on the other hand, is the moisture content within the soil stratum extending from 0 to 5 centimeters in depth. So this parameter constitutes a pivotal cornerstone for various hydrological physiochemical processes within the terrestrial ecosystem. Our study area is the region of the Orani, which is comprising all of the northeastern Algerian municipalities. The region is drought prone and is also known for its long-term drought due to low precipitation and its semi-arid climate. So the Orani is bordered to the north by the Mediterranean Sea along 400 kilometers long coastline, to the west by Morocco, to the south by Shaghi and high plains of Sirsu, and to the east by Warsanis mountains and the Dawel Shalif Valley. So it is naturally made up of coastal and subcoastal plains, mountain range, inland basins and thus steppe zone. This region is also known for its agricultural production, and it is also known for a noticeable decline within the recent past few years. The methodology used in this study is structured in the platform of Google Earth Engine to provide effective monitoring of surface soil moisture in the time series from 2015 to 2022 throughout the SMAP global soil moisture dataset and the VCI index calculated from MODIS data. So the datasets used in this study are the NASA USDA SMAP and the MODIS data that I use to calculate the VCI index. So the VCI index is, or the vegetation condition index, is suitable for monitoring agricultural drought. It compares the current NDVI to range of values observed in the same period in previous years. The NASA USDA's Enhanced MAP Global Soil Moisture Dataset provides detailed information on surface and subsurface soil moisture, including measurements in millimeters, percentage profiles, and surface and subsurface soil moisture anomalies. So the two charts here summarize the code structure on the Google Earth platform for both the surface soil moisture process and the calculation of VCI process. So we start by the Google Earth Engine inputs, which are the MODIS and the NASA USDA SMAP data, and then we proceed to determine the timeline and the study area, and then we follow by different filters. So the filter is based on date, based on image collection, and based on mean to reduce the data. So both methodologies can produce massive data. So in order to reduce the data, we chose to filter by mean, and then the outputs of both processes is the mean values of both the VCI and the surface soil moisture in the time frame from 2015 to 2022. So the results of the surface soil moisture are indicated throughout this graph and throughout the values in the table. So the values are for each year. The results showed that the mean value of the surface soil moisture anomaly from 2015 to 2022 is 0.051, which is a negative value indicating a high drought in the study area. The lowest drought was registered in 2018 with a value of 0.516, and the highest drought was registered in 2019 with a 0.069 value. As for the VCI results, so they are also showcased in this graph and in the table values for each year. So as for the VCI, the mean value detected throughout the time series was 0.56, which suggests severe drought The results are consistent with the findings of other drought studies conducted in the Algerian context in the recent years, indicating that the northern region of Algeria is indeed witnessing an increase in drought risk. Further studies are needed to identify the effects and consequences of this drought on the agricultural land and food production in the Orani area. As a conclusion, the results demonstrated that the study area is witnessing a severe risk of drought and further showcased the effective, quick, and cost-effective use of Google Earth Engine platform in monitoring the drought risk. And thank you so much for your attention.
Thank you to our colleague Rabia. If you like to share online some questions, they are welcome. Okay. It's between us, Mamoudou. Yes, thank you so much, Mamoudou. Mamoudou Senghor is an environmental analyst at the National Early Warning and the Response Mechanism Coordinating Center in the Gambia. Thank you for being with us. Mamoudou shared with us the presentation, the effect of meteorological drought on crop yield in North Bank region, the Gambia.
Thank you very much. Hello. Okay. Thank you very much and good afternoon, everyone, for having me here. It's a pleasure to be with you here. I think you'll have to excuse me of the very tired face. I am still trying to recover from a very long flight. I've been sleeping all along, trying to catch up with the Cascadian rhythm, with the change of time zone. My country is about 6 hours ahead of here. Right now, I'm trying to adjust to that. However, I will try to take you through my presentation on the topic as indicated, the effect of meteorological drought on crop yield. Already, the previous presenters have already mentioned the type of droughts that we have, their definition, and their different role as far as water management is concerned. On my part, I am just concentrating on one of the types of drought, which is meteorological drought. And this is in relation to precipitation, rainfall, the amount of rainfall that is needed over a given period of time in terms of average over a given period. My presentation can come. Okay. Yes, maybe I'll just use the opportunity while they fix my presentation. I am from a very small country in the western part of Africa. This country is about 11,300 square kilometers. It's a country that is, of course, landlocked in one way, because we are surrounded in 3 parts by a country called Senegal, which is the part of the east, west, and north. Then on the Atlantic Ocean, we have our own border. But other than that, the Gambia is surrounded by Senegal on 3 parts, from the east, the south, and the west. This is a country that is so ironical. We have a river that runs across the country, about 400 kilometers, and it almost divide the country into 2 parts. And then you wonder, why do we still have drought when the country is almost divided by river? But that is why I want to explain what we experience as a country. Oh yeah, moving. I think I have this, okay. Okay, in my presentation, I'll be looking at the introduction, the background, the research questions and objectives, as well as the results, the methodology I applied, and of course, the outlook of the research. As we all know, drought is a phenomenon that exists, and it is a slow onset, so its impacts cannot sometimes be felt immediately. but this is a hazard that affects almost a large number of the population in our country. And this is a country where we have 30% of our GDP is contributed through agriculture, and 70% of the employed workforce are engaged in agriculture. So agriculture is very important to us. And on my research, I am looking at 4 cash crops, that is early millet, sorghum, maize, and groundnut. These are the 4 main crops that we grow in our country, and some other vegetable crops and other things. But hope my presentation is not also affected by the Cascadian rhythm. It's trying to adjust to time, huh? Yes, the definition is just there. We have meteorological drought. It's a complex and natural hazard that is global in nature and has threatened the livelihoods of Gambia's most vulnerable population, specifically the region where I come from. And this is the region where I do this research for, which is the North Bank region. Is one of the 6th administrative region of my country. And he said we have only one rainy season that range from June to October. And between this rainy season, it is a very short period. We have a long dry season, which is sometimes an impact, where the country is mainly we depend on mainly rain-fed agriculture. We don't have much irrigation. All the farmers, most of them, 99%, depend on rain-fed agriculture. So in a country where you have only one rainy season and it lasts for only 3 months, and this is a problem. So the Gambia is particularly prone to drought due to its location at the southern fringes of the Sahara Desert. I just mentioned that the Gambia is surrounded by Senegal, and this southern part of the Sahara Desert is crippling in towards the northern part of the Gambia. If you look at the map there where I mark red on the map down, that is where the region that they conduct the study for. And this part is mainly affected by drought because of the crippling effects of the Sahara Desert that is running from the north. And we have about 10 rain gauge stations. The country is a small country. We have about 10 stations that cover the whole country. And the stations that I am looking at is in Terawan, which is the North Bank part of it. And North Bank is one of the 6 primary administrative regions, as I mentioned, with a population of approximately 21,000. Yes, 221,054 people. And among that, we have 2,255 square kilometers according to a 2003 census. Move on. Okay. The methodology we employed in this research is trend analysis, correlation analysis, and regression analysis. And in the trend analysis, we try to answer the questions: how has crop yield varied over a period of 30 years from 1987 to 2018? And also, how has rainfall varied over that period? Also, how has this rainfall affected the crop yield? That is the correlation and regression between these 4 cash crop and rainfall within the period that we conduct the study. The other methodology, we have the SPI, that is the Standard Precipitation Index. Somebody already defined that. We've looked at the range from less than, greater than 2, we said very wet, from 1.5 to 1.9, then from 1 to 1.49, moderate wet, then 0 to 0.99 to minus negative is normal, then -1 to -1.49, moderately dry, from 1.5 to 1.99 negative, severely dry, and from less than -2, we said extremely dry. And this one is used to provide early warning and severity as it is specified drought condition for each location, as well as for risk management. So the advantages of SPI are the use of longest time scale to approximate of groundwater and stream flow drought. However, the limitation of this index include the possibility of trend in precipitation and adequate observe of data during this period. This is the trend analysis of the 4 cash crop that we studied on. Early millet, we have late one, but I studied on the early millet, the maize, the sorghum, and the groundnut. In the trend among the years from 2006 for the maize recorded the lowest, and around 1992 to 1994, that is 1993, it recorded the highest, which occurred around 2002. Also for groundnut, the rainfall data, the cash crop data for 2002 and 2018, we are challenged with data and which is always scarce in some part of our developing countries. So for groundnut, I was just able to get data from 2002 to 2018. And of course, this has affected the correlation and regression analysis between the groundnut yield and the rainfall patterns. And sorghum also is a type of cash crop that we grow in the region as well as early millet. Yes, this is the variability of rainfall over the period from 1987 to 2017, as I mentioned. So among these years, the lowest rainfall was recorded in 2011, which indicated a very severe drought. It has seen close to -2, which indicates a severe drought. And the highest was just recorded about 2-3 years after in 2015. So using this standardized, the result shows that the lowest rainfall, as I mentioned, was in 2011. And the results also shows years of below normal rainfall with respect to the standardized normally of a mean of 0. Somebody mentioned the threshold, but this one we just use a mean of 0 and a standard deviation of 1. So this is a correlation and a regression analysis. Correlation and regression analysis between these 4 crops and rainfall. And I'll just concentrate on the p-values, which explains the relationship between these these 4 crops and rainfall. For early millet, it explains 0.21, which is about 21%. And since it is less than 0.05, then my hypothesis is rejected. And it's the null hypothesis, it indicates that there is no statistical significance correlation between below normal rainfall and yield of the 4 major food crops. Then among the 4 is only that maize, which indicated a correct hypothesis for 0.03. That indicates that there is no statistical significant correlation between below rainfall and that. So the research is needed to fill the gaps, understanding the different types of drought in the region, because this research is mainly on meteorological drought. If you want to look at hydrological drought, you will have to consider soil moisture, and where we have data challenges. So the use of space-based technology will help in having access to soil moisture data and other data that we can use, temperature, and so on, to be able to determine the other factors that can affect crop yield other than only rainfall. Because the cash crop that we grow within a period can really depend on the rainfall that is available. But the other factors in terms of soil types, soil moisture, and other things could also be studied further. And this will help in planning for drought mitigation. It is important to understand that drought characteristics through drought analysis development of national programs can be informed by experience of regional drought management. So in conclusion, drought analysis over the area of studies vary between mild drought and moderate dry condition. Given that these are rainfall seasons and such, the condition might worsen during other dry seasons, reducing the risk. Therefore, impacts of drought of utmost importance and require great emphasis. So with space-based technology, it can help in prediction for future drought and help in policy development and decision-making for our developing countries. So thank you very much. That is what we have.
Thank you, Mamadou. If somebody have one question, too.
Yes.
Thank you.
Yes, ma.
Well, thank you very much for a nice presentation. This is Mandira Singh Shrestha. I come from Nepal. I'm equally jet lagged as you are. too.
Yeah.
But regarding the comparisons that you made for the 4 different crops, you've used the rainfall data you mentioned.
Yes.
So where did you get the rainfall data? Was that in situ data along with the satellite-based observations? So that's one question. And out of the 4 crops, I also noticed that only one crop, that is sorghum, that has an increasing trend versus the other 3 that have a decreasing trend. So would you also explain why that is so?
Thank you very much. The rainfall data used from this is from an in situ station in Karawan. That is the only station in the region actually, which is very sometimes challenging. And it is collected by the Department of Water Resources and stored locally in computers just like that. So access to satellite data is available, but this is through a regional block by the agreement where we have access to these things. It will help in forecasting for the rainy season. But that is the only thing that we use that particular data for. But as we speak, we are looking forward to developing satellite data and getting access to it also with some little bit of capacity building and so on needed. Yeah, but the data is from in situ data. That is data from a weather station that is recorded and sent to a central server, and that is where we can have access to those data. On the type of crops, I already indicated that the only accepted hypothesis is for sorghum, which indicates that there is no relationship between rainfall and its yield. But also, I mentioned that there could be other factors that affect the yield of crops other than only rainfall, ranging from soil types, soil moisture, and fertilizer. Because most of the people that are farmers there, we depend on these inorganic fertilizer, and its availability is sometimes very expensive for the local farmers, which they used to grow their crops. So other factors could be the reason for the decline of those crop yield. Yeah.
Thank you.
Yes. Nina.
Maybe I shouldn't be asking questions, but yeah. My question relates to the resolution you would need for soil moisture data sets. I think that relates to the size of the fields also that you have in Gambia. So maybe you can elaborate on that, because there are global soil moisture sets that are available.
Yes, soil moisture data is just recently that we have been donated a station that is automated, that can also have sensors of soil moisture that sends information by the Cima Foundation of Italy. If anybody have access to those ones, they help us with a station that monitor those things. But as we speak, that is very difficult to have soil moisture data in those areas. This is why the study just focuses only on rainfall, but we could have, in further studies, included soil moisture, which is, of course, available through satellite data and images that we can also explore in the future. Thank you very much. Yeah.
Thank you. Thank you so much. Was very interesting read about the increase of productions, no, in some special during drought periods. And you say there is different types of drought in the region. Can you tell us about this
Different
kind?
types.
Yes.
Yes, I just meant somebody just presented on all the 4 types. That is agricultural drought, hydrological drought, and the socio-economical. In 2011, we were hit by a drought. That is according to the presentation. We have registered the lowest in the region, about 533 millimeters, which is quite very low. And what it led to is socio-economical drought, which is food insecurity. The absence of all these cash crops in the region has affected the population a lot. So that is the impact of meteorological drought leading to a socio-economical drought, which is the absence of one of the crops or 2 or more crops for consumption. And for hydrological drought also, that could lead to soil moisture, and we are finding it challenging to have soil moisture data, as well as agricultural drought. So hydrological drought leads to the subsurface and surface water bodies, and the agricultural drought deals with the soil moisture. Maybe further studies have to be conducted with the access to data from satellite images that can help in maybe expanding on the study. Yeah, but of course we are affected by socioeconomic.
Thank you, Momodo.
Thank you.
No.
Thank you.
Okay, thank you so much. I can see that our next presentation from Ghana with Bernard Michel Agwasi. There is a recent graduate with the Master in Environmental Engineering and Management from the University of Energy and Natural Resources. Welcome, Bernard.
Thank you.
And Bernard talk about the geospatial mapping and analysis of surface water. Thank you so much.
Thank you. All right, hello, everyone. My name is Bernard Ochre once again. Yeah, it's unfortunate I couldn't make it on site, but here we are. Let's go. Let's do this. All right. So can you all see my screen? Share my screen. Okay. I got it. Relax. Okay. All right. Okay. Please, can you all see my screen?
Perfect.
Yeah. All right. Let's do this. All right. So my name is Bernard Michael Akwesi from Ghana, and I'm here to present on the topic geospatial mapping and analysis. Someone's on my slide. Okay. I'm here to present on the topic geospatial mapping and analysis of surface water demand, abstraction, and water yield in the Tana River Basin of Ghana. This project was funded by the Regional Center of Energy and Environmental Sustainability of the University of Energy and Natural Resources. All right. An overview of water resources in my country, Ghana. Ghana has a land area of about 240,000 kilometers square, with three main river systems, namely the Water River System, the Southwestern, and the Coastal River System. And then the catchment area of where my study was conducted is part of the Southwestern Basin, which extends a little bit into Cote d'Ivoire of an area of about 15,000 kilometers squared, sorry. In Ghana, river basins serve as critical sources for various uses, including human consumption, agricultural consumption, and industrial consumption. Now, why this study? The Water Resource Commission of Ghana over the years have stated that the Tana River Basin is one of the most exploited water-stressed basins over the years, and it is posing a threat to effective management of its water resources. Again, the Water Resource Commission are also saying that the Tana Basin is facing increasing demands due to factors like population growth, agricultural expansion, urbanization, and it is resulting into potential water stress among different water users. Unfortunately, the existing studies are limited in providing a holistic evaluation of water stress, considering factors like population growth, agricultural practices, industrial activities, and climate change impacts. With these being established, my main objective was to comprehensively assess and to spatially analyze surface water dynamics, including demand, consumption, withdrawal, and availability on the Tana River Basin of Ghana. Specifically, to conduct an inventory and mapping of water abstraction among different water users in the basin. Secondly, to estimate and map current water demand, assess its impacts, especially on projected climate changes on future domestic water demand, and also to determine the water yield in the Tana River Basin, and finally, identify the potential water stress areas in the basin. My study area has a bimodal rainfall season occurring from April to July, which is the primary season, and then the secondary season occurring from September to November. My study area also supports residential, agriculture, and mining needs. All right, so water abstraction is basically defined as the act of removing water from a particular source or natural source. And in order to achieve this objective, an inventory analysis was conducted at all the various sectors to ascertain how much is being abstracted based on factors like the pumping capacities, the number of pumps, and the pumping hours. Okay, these factors were used to, estimate how much is being abstracted from all these sectors. Okay, then the estimated values, as you can see from the graph, were then incorporated into the GIS software, also based on the GPS coordinates of all these abstraction points. And then a map for domestic, industrial, and irrigation water abstraction maps were then generated. And then finally, a total abstraction map was generated. As you can see, these are all the abstraction points in the Tano River Basin. And the pictures are clear indication of the inventory analysis we conduct with the help of the Water Resource Commission in Ghana. Water demand is simply the amount of water required by individuals, communities, industry for their various purposes. And then in order to estimate our domestic demand and industrial demand, the following equations were used. That water demand was also estimated using these following equations. It is widely accepted by professionals. Finally, again, water yield is water that is readily available for abstraction. And in order to achieve this estimation, the soil water analysis tool was used based on requirements like the DEM, the digital elevation model, the land use, land cover, soil map, slope, and then data and weather data, which is precipitation and temperature from NASA power. All right. And then the model analyzes water yield using this equation below, as you can see here. The water yield for each sub-basin was further multiplied by each sub-basin to get the actual volume of water yield in all the sub-basins. And interpolation was also incorporated here to get the total volume of the entire basin in general. All right. And then finally, water stress is also defined as a condition where the demand for water exceeds the available supply for water. And then the analytical hierarchical procedure or process was used based on these criteria: the total water yield of the basin, the total water demand, the total water abstractions, and population. And as an AHP, as demanded from an AHP, a pairwise comparison metrics were done based on expert judgment and the calculation of weight. And then the GIS was used to do the standardization and the weighted overlay analysis. And then finally, with a consistency ratio of 0.6, which is very good for our analysis, a potential water stress map was generated. Okay, so the following figures and values are, results from the estimations and then mapping of water abstractions and demands, showing how demand and abstractions are distributed in the basin, ranging from very high and very low values. So for example, domestic abstraction in total was 4.8 million meter cube per year. And then the map is showing areas where very high abstractions for domestic is done. For domestic water demand, a total of 63.87 million meter cube was reviewed. And then for industrial demand and abstraction, a total of 52.8 million meter cube was reviewed. For livestock water demand, 1.8 million meter cube per year was also reviewed. And then for irrigation, 151.41 million meter cube was reviewed. In the estimation of total water abstraction, it was revealed that the agricultural sector is the highest water consumer, followed by the domestic and then industrial. And this findings corroborates with global studies that agriculture sector is the highest water consumer. And we came up with a total value of abstraction of 210 million meter cube per year. In the estimation of projected domestic water demand, the graph here is showing how domestic water demand is set to increase from 2030, 2053, and 2063. The regression analysis to ascertain the impacts of future climate changes and domestic water demand also gave these graphs showing that both rainfall and temperature will significantly affect water demand for both RCP 4.5 and 8.5. But comparatively, temperature will significantly impact domestic water demand very, 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 very high as compared to the rainfall, all right, based on their R-squared values and then their p-values. In the estimation of water yield, a total of 5.9 billion meter cube was estimated as, total water yield for the basin. And then the graph is showing the various water yield from 2012 to 2022. And then the graph below too is showing how the various factors that contribute to water yield affect water yield. So it is obvious that the higher the rainfall, the higher the water yield, and then vice versa. And it also agrees with a lot of studies indicating that rainfall is a significant contributor or contributory to water yield. Yes, obviously, before any model can be accepted, it has to undergo calibration and validation. And then with our R-squared values, we can all testify how credible my model is into the estimation of water yield. Finally, the potential water stress assessment also revealed that about 41.7% of the basin is approaching moderate stress, followed by 39.7% high stress, followed by 14.69% low stress, and then 3.84% very low stress. And a small significant amount of value is approaching a very high stress. So as you can see on the map on the right, other hand, are various districts that are approaching the various kind of stress levels in terms of water. All right. So to conclude, the study has revealed that or has called for attention for sustainable agricultural practices to ensure the effective use of water in the agricultural sector. It has also called for the attention for immediate climate attention or action or mitigation to curb the future impacts of temperature on domestic water demand. And I think it also aligns perfectly to the purposes of this conference, where we need space technology for effective water management. So I think to conclude, I think it is obvious that these findings are very vital, and then further studies should be done to make it more impactful. With these, I think it's okay to conclude. Thank you very much. Thank you very much. Is there any questions? You're welcome to ask any questions thank you.
Thank you so much, Bernard. Maybe there is a question online or in the auditorium. Yeah, you like it? Thank you, Mandira.
So, good afternoon, Bernard.
Good afternoon.
Thank you for your presentation. You mentioned that you have used future climate projections as well as the different scenarios, 4.5 as well as 8.5. So Which data sets in particular were you using for the future climate projections, and how do you select the particular data sets for this particular study? Because there's
Okay, thank you.
projections that are available, so which did you find appropriate for this study?
Okay, so with regards to the climate data sets, I visited the climate change assessment portal, the CCAP, and then a bias correction. It's already correct, like the bias correction has already been done. Okay, so I selected that from using 22,000 as my baseline. Okay, and I selected these climate change for both RCP 4.5 and 8.5 to be analyzed. So I think that is where I took my data from, climate change assessment portal. That is where I got my data from to be analyzed for my domestic demand and its impact on its, yeah. Thank you.
Thank you so much. Maybe online I can see to Lonely Mambo. You have a question online? Can you open your microphone? It's possible.
Yes, can you hear me?
Yes, please, I can hear you.
Okay, great. My question is, it was actually for the previous speaker, but I just want to say for Bernard, it's a great presentation. Thank you so much for sharing that. Wonderful. But my question is for the previous speaker. I wanted to find out if sorghum is a staple food in Gambia. And if so, let's see, what is this? Okay, if so, considering climate issues, is there ever a concern of running out of this food source? And what is the mitigation plan?
Thank you.
Thank you.
Thank you.
Yeah, thank you. Hello,
We can listen.
it's on. Okay, thank you very much for the question. I want to know the sorghum you asked is referring to the cash crops, but generally, people grow it in small scales compared to the early millet. We use coos as our staple food, that is coos, but generally it is used using the early millet, and a portion of the sorghum is used. According to the research, sorghum does not, the low rainfall does not affect sorghum, so our advice or recommendation could be to shift our attention on crops that are drought resistance, that is the likes of sorghum and other crops. Those are the mitigation plans and recommendations as far as the research is concerned.
Thank you.
Thank you. Thank you. Bernard, is very interesting your idea to the urgency to implementing sustainable water management, no? And some strategies to address the water scarcity in the Tano River.
Yes, please.
I have a little question about how maybe you think help to the decision makers to talk about this inequity, in particular for the irrigation demand. What do you think?
Yeah, so as part of the study plan, yeah, we will have a session with the WRC, review our results to them, and then we find a way to communicate the findings to them to help curb this situation, because the amount of water these agricultural people are extracting is very outrageous. So as part of the study plan, it is yet to be communicated to the Water Resource Commission. They are solely in charge of water resources in the country, so that from there we will see how best this study can help mitigate the outrageous use of water in the agricultural sector. Yes, please.
Thank you. Thank you so much. Well, it's interesting to find the different approaches and diversity in the types of these four analyses, no? Vapor pressure deficit, Google Earth Engine platform, assess and geospatially analyze surface water dynamics from the identification of information sources, such as data processing at different scales, basins, municipalities, crops. Indeed, each of the cases show us in this session the need to provide information with the least uncertainty and the appropriate methodology in each case. And with the main challenge to the correct proposal, the use of information to promote risk reduction in making decision. We hope in this session that the audience has inspired and connected the dots to continue with the new and innovative research that allows the solutions of these kind of global problems. Thank you so much.
Thank you too. Thank you for having me too. And I hope there will be a new and the next on-site session to have me on site. Thank you.
See you soon. Thank you so much. Okay, I understand that the next step is a break. Yes? See you soon in 30 minutes, maybe.
Recording stopped. Recording in progress.
Expo is online, just follow from the book Vienna, followed by online.
From a show for
Yes.
Okay. And then
So,
good afternoon, colleagues and participants. Welcome to this technical session that we'll have at this second part of the afternoon. The session will be focused on the topic informed decision making for agriculture interventions and irrigation decisions. I'm honored to be the moderator of this session, which will delve into some cutting-edge advancement and innovative projects aimed at enhancing agricultural productivity while addressing sustainability and water management challenges. We have in the program 5 presentations, but one of the participants, I think, experienced some difficulties to be present with us today, so we will have 4 presentations in this session. The goal of this session is to explore how technology and data can help and support us to address some of the most pressing issues facing agriculture, such as food security and sustainable water uses. The first speaker in my list is Jorge Guterres from the FAO, Food and Agriculture Organization. And the presentation will be on the program called VAPOR project, which uses a publicly accessible near real-time database to monitor agricultural water productivity. Jorge Guterres, the floor is yours.
Thank you so much, colleagues. It's a pleasure for me to present today the WAPOR project. This project is a project of FAO and stakeholders for 3 institutions research. This project began 2 years ago, and for Latin America and especially for Colombia in the last year. The project is very interesting because have a dialogue with this kind of issues. Over 200 million people suffer for hunger. Around 3.2 billion people live in agricultural areas with high to very high water shortage of scarcity. Agricultural production needs to grow globally by 50% to 2050 in our informed to state of the world and water resource. And from 2000 to 2018, total cropland increased with 63 million of hectares. Almost 85% of this increase in the irrigated. In general, this project use information about remote sensing for water productivity. That is an indicator that can be used to monitor, at the same time, progress and spatial variation in terms of land productivity, biomass, and yield. And in water being consumed to obtain these yields, both terms of equation are important and need to be looked at together. Making the most out of every drop of water is a target that makes sense across scales and across water users. The project was founded by the Netherlands and has 2 main partners. One institution, one of those is INWI. There is 2 colleagues here. It's a pleasure to meet in person. And the IHE Delft, that is an institution of education, water, it's important in the world and is a UNESCO institution. And one service provider called ELIF. From satellite images, our algorithm calculates parameters of interest such as biomass, evaporation, and precipitation, as well as other climatic parameters from which we can calculate water productivity and do water accounting at the basin level. That is very important for some researchers. The WAPOR portal provides data in near real time. What it means, every 10 days, since 1909, we have 3 spatial resolutions. Fortunately, today we have 300 of size of pixel for all the globe. For some countries, we have 100 size of pixel, and in some cases for each countries, we have 1 or 2, or in some cases 3 analysis for 20 meters. And I invite you to show in each country what kind of measurement you have, no, in your institutions. Really, these are very, very good information disposed for the project, and for free database. Okay, this is like you can see in the third level, that is subnational level, no? 20 meters for size of pixel. Okay, what is the data in the database and in the portal? Now we have water productivity, actual evapotranspiration, reference evapotranspiration, precipitation, relative root zone soil moisture, that is new, net primary production, and some quality layers. And the temporal resolution is very interesting because we have decadal, each 10 days, monthly, and annual time steps. You can see now in Colombia for South America. It is very interesting for our Latin American, Caribbean countries, because in this way, for example, the institutions and partners are translating the information and the course and the manuals to Spanish, and it's important for our region now. Okay, this second phase began in 2021, focuses only on the expansion of the spatial and temporal coverage of the database, but on supporting countries so that they could use web or data to capacity development and of tools or solutions together to respond to challenges that the countries themselves identify. This is very interesting because, you know, in each country there is a research in particular or have a special difficulty, and then we use in each case some road different when depends of the what is the research, you know. Okay, and I say WAPOR is open data access. What it means, have a methodology, documents, manuals, quality assessments online. You can to download each document, each process. We have the codes and algorithms online. We do trainings to our countries. You can to see data and metadata available in the portal, and you can indeed navigate the portal. You maybe in this moment have two versions, the and the third version now, with some variables in use. And as I say, we have open geospatial standards, and you can use all this kind of information for your countries. In the same way, there is available resources for capacity development. We have courses, all the database in GitHub, and we use Python for the programming. And now the idioms, English, French, Arabic and indeed Spanish. You know? Okay, what is the main idea of the use? We are talking about the different scales. Policymakers is one of these, because the idea is to understand where and, for example, in which kind of crops use this information. The second one is the irrigation schemes managers in basins, for example. And finally, and it's ideal to find farmers and identify end users for develop apps. For example, in other countries, there is like 6 or 7 apps that can be used the farmers directly. Some applications, in this case, we use this image to share performance indicators to understand variability, and you can separate each variable and analyze, for example, in this case, a specific basin and to identify what happened with the field production and the water productivity in some special case. It depends of the research, you know. Another application, we have this gift using in Mali irrigation Niger information, and shows the evolution of water consumption between 2009 and 2018. And it's interesting because in this case is in the better scale, 20 meters. Finally, I show some application in Egypt, Lebanon, Tunisia, and Jordan. It's another case. We developed AWP application, for example, for using the data, and no less important, to help the countries to measurement the SDG indicators 6.41 and 2. And in our case, in Colombia, for example, we are very focusing in drought because the El Niño phenomenon in these days. Now you can see Colombia and Africa in this kind of assessment. This is an animation about this relative root zone soil moisture that evaluate upper 200 centimeters of soil making in the vital of the plant growth and ecosystem health. Some phases in the training workshops, and the idea is that you can see and navigate and download the manuals and database and make your own questions for the data portal. Thank you so much.
Thank you, Jorge, for this presentation. I think Vapor is one of the most important projects that was initiated and developed by FAO. And as it was demonstrated from the examples shared during this presentation, there is a lot of applications, a lot of impacts that this kind of application could bring to the agricultural activities. We can maybe open the floor for 1 or 2 questions from the audience on the presentation before moving to the second presentation in this session. Yes, please.
Thank you very much for the nice presentation. I'm curious about something very small. Why the resolution changes from country to country?
It's a decision of the project because we need to prove and to understand what happened with some special cases. Really, we are understanding and learning what happened with this kind of basin or latitude and longitude. Yes, we try to understand what happened, but in general, the most important is all the globe have 100 meters, and 30 countries have 100 meters. Okay.
Yes, one more question.
Buenas tardes, mi nombre es Eddie Romero de Costa Rica, Senara.
Good afternoon. My name is Eddie Romero from Costa Rica, Senara. The possibility of implementation in Costa Rica of the program with FAO, what is required for that? That question has been made previously. For the colleagues that are in Latin America and the Caribbean, we have a regional focal point and one in Mesoamerica, in Panama, and we are making the dialogues and expanding the resources that are available. They go all the way to 2025, sorry. So what we're doing is we're starting to expand the trainings. I think that very surely the growth of the use of the application will go somewhere there, which is already an advantage for us, the Spanish speakers, that the course now has. For example, it is now open in Intel and it is in Spanish, and you can download it, you can do the courses without any problem. So we're going to have the biggest possibility of working with that.
There's a very famous movie called Lost in Translation.
Y hay una muy buena película que dice Perdido en la traducción. ¿Puede resumir para que todos los participantes puedan también responderlo? Nuestro colega preguntó.
For example, if we in Latin America, how can being the route to implementation, and I say that exactly there is an advantage now because for Hispanoparlant, we have now in HEDEL a Spanish course, and it's free and can to download and to join to the course. Excuse me for switch to Spanish.
Yes, please. Do you have a question? Yes, please. Here. Okay.
Hola, hola. Sí. Muy interesante tu presentación, de verdad, me gustó mucho.
Your presentation very interesting, very precise and simple. I'm going to do it in both languages. I would like to know if the application is a FAO or is it a group free, and can you adapt it to multiple platforms or devices?
I love your presentation, very high quality, very precise. I want to know if your application is free or we must pay a fee for using different platforms or for different users. After my question, the lady.
Thank you for your kind question. Yes, this is a frequently a question when we present WAPO, because you know the use of another kind of information is for pay, no? Now precisely the advantage for WAPO is that the information and the database is it's an open access database. You can use the data that is available for the countries. I say for Colombia in Latin America and Caribbean is information by 100 meters for the pixel size, and for African countries and Middle East is in some cases for all the 12 with calculated field countries available in this size of pixel, no, and it's for free. Is open access database.
Just a quick clarification for the answer to the first question that was asked. You said in general, all over the globe, there is 100-meter resolution, and in 30 countries there is
300 meters of resolution all the global.
Okay, thank you.
Yes.
And in 30 countries, it's 100 meters.
100 meters.
Perfect, thank you.
Maybe last question from this lady.
Thank you for your presentation. One thing struck me, you said there's action-oriented data for different users. And you gave examples of farmers, as well as, I think, irrigation scheme managers, and also decision makers. So I was wondering how that information or data is made accessible, one, but is understood by all these different users. You know, how is it communicated to them so that it is action oriented for all the different users? Because the understanding by each of the users would be different.
Thank you. Good question. Yeah, this is the main challenge. You take the point, because it is easy to bring, for example, training for experts, no? But you know, our farmers and maybe the decision makers don't have this kind of expertise. But the challenge is how to put it together in a dialogue table of interchange of knowledge. There is the challenge of each coordinator by country. In my case, in Colombia, for example, in my case, we do training workshops both, no, together, and it's a challenge.
Maybe to bring some complementary information to your question. The system is providing different kind of indicators. Some of them are used by farmers and some are used by decision makers. For example, when it comes to the water productivity is something which is more used by decision makers to know if it's worth to invest in irrigation in this area, knowing that the productivity is low or high, etc. This is information which is dedicated to a decision maker, for example. When it comes, for example, to managing irrigation at the farm level, for example, water consumption is one of the information provided by this system, is more easy to use by farmers than by decision makers. So the system is providing a list of indicators which are different with different information, and each component or each group of these indicators is used by different kind of users. Could it be decision makers, farmers, water authorities, etc.?
Thank you for complimenting.
Yes, please.
Thank you. Who was your process to validate the actual evapotranspiration in Colombia? And the other question is, what was the approach to estimate the different variables to relate it with actual evapotranspiration? Was the for energy approach or mass approach?
Yeah, thank you so much. Because you touched the validation process, and it's very important because we are talking about the reduction of uncertainty, no? Yes, there is a process in the between the L2 and L3 layer, and if you can do access to L3 layer, you need to take data in field. Yes, and the focus of evapotranspiration is the FAO focus biomass.
Well, once again, thank you very much for your presentation, and from the questions raised by the audience, I think subject is very important, and there's a lot of interest in this discussion. The second presentation speaker in this technical session is Mr. Karchikian from CGIAR, and he will present presentation on the sustainable agriculture in the lower Limpo Basin, focusing on irrigation performance in Mozambique. Thank you.
Thank you. Thanks, Jorge, for setting up the scene. Basically, we are working in the same project, but in different countries. So my presentation is basically a continuous, Jorge's presentation. And there were many discussions about how the data sets that are available in the portal could be potentially used for some specific applications. So the work I'm going to present is a specific applications that has been currently implemented in Mozambique using the WAPO data with the stakeholders. Yeah, we all know the challenges ahead in terms of the irrigated agriculture. Like we have been discussing from the morning about the challenges of optimizing the water use within the agricultural system, and Mozambique is even not an exception. They have a unique set of challenges in terms of, for example, Mozambique is one of the downstream countries in the lower Limpopo River Basin where they are subjected to floods, but in case of the upstream countries, floods are not a major issue, but droughts are the issue. And Mozambique has invested quite a lot on irrigation infrastructure, particularly in the lower Limpopo River basins. But then these irrigation schemes have undergone a lot of governance in terms of, for example, these were set up as primarily a public irrigation systems, but then in between it has changed to smallholder systems. Now it's a mix of both public irrigation as well as smallholder irrigation systems. And now there is again a further change in terms of moving from, for example, they are renting out a lot of irrigated areas to big private companies. At least 50 to 70% of the irrigation schemes areas are rented to the private companies, but then the remaining 30 to 40% schemes are still under the smallholder systems. So there are a lot of governance challenges and the way in which the governance is also evolving in these irrigation schemes in Mozambique. And of course, because these schemes are spread over 40,000 hectares in the lower Limpopo, there is currently no monitoring system in terms of how these irrigation schemes are performing in terms of its intended objective when it was designed. So when we started working with different stakeholders in Mozambique, so the way in which the FAO, for example, the WAPO project works is that we go into the specific country and we interact with the different stakeholders in the specific countries, including different government institutions, private sectors, universities, and research institutions to identify a broad set of challenges that could be potentially addressed using the WAPO datasets. Once we identify a broad set of challenges, usually when you ask them what are the specific challenges that you need to be addressed at a country level, then you get challenges which may be addressed using WAPO data and which may not be addressed using WAPO data. Then we try to prioritize a specific water resources challenge that we could address using the WAPO data portal, and we try to engage with the relevant stakeholder who are responsible for addressing that specific challenge. For example, in terms of this specific case study in Mozambique, when we identified that the stakeholders are interested in assessing the irrigation performance of these big irrigation systems in the lower Limpopo, we identified two stakeholders within the Ministry of Agriculture. One is INIR, which is responsible for the irrigated areas in the lower Limpopo, and then the second one is the irrigation scheme managers. The irrigation schemes are now in quasi-government entities in the sense that it's both government as well as public. So private, so they've got a 50-50% share in that. So these are the two primary stakeholders we are engaging now in terms of co-developing this tool. Jorge mentioned about this WAPO database. Just to sum it up, his presentation, WAPO is basically a database which provides you a free access to a land and water productivity indicators. When we say land and water productivity indicators, there are two primarily important data sets in the WAPO portal. One is the crop water use data, which tells you how much water was being used by the crop. And the second one is the net primary productivity data, which basically tells you how much carbon has been assimilated in terms of production of the crop. Essentially, you can convert this net primary production into an biomass production, that means the crop yield. So in essence, WAPO provides two critical data sets. One is how much crop water is being used. The other one is how much crop is being produced, right? In essence, that's what the WAPO data does. And you also have another, what we call as different indicators like precipitation derived from chirps or reference CT derived from, for example, the FAO portal. And there are different data sets which are derivative of the other data portals. And these are made available at three. I think there was a talk about the spatial resolution, why the spatial resolution changes over different countries. So for the global, the spatial resolution is 300 meter by 300 meter. But then for specific countries, it's 100 meters. And these specific countries, the whole of African continent is covered by 100 meters. And there are a couple of countries outside the African continent, particularly Sri Lanka, Pakistan and Colombia are covered by 100 meters. But then there is a third level of data set, which is the highest resolution of the data set, which is the 20-meter resolution. And that is being covered only for a very, very small focused area within each of these countries. For example, in Mozambique, the entire Mozambique is covered by a 100-meter data set. So whatever the data sets that Yoge has listed is covered for whole of Mozambique at a 100-meter resolution. But then for the specific areas where we are focusing on the lower Limpopo, it is covered using 20-meter resolution. And the reason is that because of the cost, right? All these data sets are processed in the cloud, and there is a cost associated with processing these huge high resolution data sets at a country level. Unless there is a specific need from the stakeholders, it is extremely prohibitive to process this data set for country level at 20-meter resolution. That is why the data sets are available at 300, 120-meter resolutions for different levels. Again, these data sets are available at different temporal resolutions. One is decadal, every 10 days, monthly, and then yearly time scale, right? So this is second phase of the Vapor project. The first phase mainly was like a proof of concept phase where the portal was developed and we tried to pilot 1 or 2 applications. The second phase focused primarily on how this data could be used for operational applications in different countries. And these are the sort of a bottom-up approach where, for example, the FAO basically is in charge of the overall project and then developing and maintaining these databases, while IHE focuses on capacity building activities, and EME International Water Management Institute, where I come from, focuses on developing a specific stakeholder-centric applications using the datasets from the Vapor portal. And at the moment, we are working on at least 11 countries as of this month, working with different set of stakeholders, developing different type of applications, including some of the mobile apps that Yoge has showed in his presentation. So our scale sort of moves from national scale to farm scale. In the farm scale, most of the times our focus is on irrigation scheduling, which is being piloted in Palestine and then in Tunisia at the moment. But then in a number of other countries, our focus is on a system scale. We are focusing on specific irrigation systems like what we are doing in Mozambique. But then in other countries, we are also looking at the national scale, looking at for example, the water accounting and about water budgeting aspects of it using the Vapor data. So basically the way in which we approach this is once we identify a specific solution, specific challenge to address and specific stakeholder, we organize a series of meetings with them, try to co-develop these solutions in terms of what they expect from these solutions. So instead of we trying to sort of create a solution for them and giving it to them, we ask them, okay, this is a challenge you want us to address. And this is these are the data sets available in the Vapor, how we can go about it. So what sort of applications they need and what sort of outputs they expect from it. And then we have a series of meetings with them. We try to co-develop it and brainstorm it. And then eventually we come up with some sort of a very skeletal framework which looks at this. So basically this is performance indicators that we derived from the Mozambique stakeholders for this particular applications. So when we are looking at this irrigation schemes, most of the common indicators, for example, focuses on the crop water use, how much water is being used by the irrigation scheme. And then they also need an information on the crop water requirements, economic water used, basically the economic water productivity, system efficiency, right? And then crop type mapping. We have to note that not all of the indicators could be eventually derived from the Vapor. Some of these indicators can be derived directly from the Vapor. Some indicators need field level data sets. Some indicators, for example, crop type mapping, need a separate level of activities, right? So then we basically try to identify what sort of data sets that are available with the stakeholders, and then we try to develop these indicators. At the moment, we are focusing on developing the crop water use side of analytics and how this can be scaled up to a number of irrigation schemes across Mozambique. So this is basically the framework in terms of how the tool will extract the data from the Vapor portal automatically using the API, and then it will create a set of remote sensing based indicators. And then also when we get the data from the stakeholders, it will combine the remote sensing based data sets with the field based data sets to derive indicators in terms of the system efficiency, in terms of, for example, the trends in the crop water use, the seasonal water use, or even annual crop water use. So at the moment, we are looking at 10 irrigation schemes with combined area of almost 90,000 hectares. But at the moment, in this today's presentation, I will just show some of the results from the Chokwe irrigation scheme, which is the largest irrigation scheme in Mozambique with 40,000 hectares. As you can see, Chokwe irrigation scheme is basically located in the lower Limpopo Basin in the southern part of Mozambique. And it's around 40,000 hectares. It consists of sort of three sectors and then multiple blocks within it. We did not go into the farm level water use before because at the time the resolution was at the 100-meter resolution. The level 3 resolution was not available, so which was not really suitable for the farm level applications. But then now the level 3 data, which is at 20-meter applications are maybe 20-meter data sets are made being available. So we are basically moving beyond the block level to the farm level water use. Now, instead of 3, we are moving to the 4th level of water use, which looks at scheme, sector, blocks, as well as farm level. Again, one of the requests from the stakeholder was that since this is a quasi governmental organization, they are being charged by another organization for the water use. But then they don't have any specific estimates of how much water is being used within the irrigation scheme. By employing the WAPOR data, we provide them how much water is being used within the irrigation scheme on an annual basis so that they can compare it with the organization they are charging the data sets for, right, in terms of the amount of water used. So this is a seasonal water use in terms of the annual time scale. So you can also look at spatially how the seasonal water use sort of changes, evolves over the time period. Sorry, this is from 1920 to 2020-21, and we also have most of the recent data sets available. Again, you can look at the seasonal water use in a very, very different way. So, for example, whether these water use are distributed equally among the different locations of the irrigation schemes. And you can see that when you look at the equity of the water use, most of the times the water used, the equity of the water use is generally poor, but except in one instances where it's generally fair, it means that the irrigation scheme is not yet performing to the optimal level. Again, it's another indicator in terms of the beneficial fraction. Basically, beneficial fraction looks at when a certain amount of water is being used by the crop, how much is the transpiration component of it, and how much is the total ET component of it. It just looks at the ratio between the transpiration and the ET component. And you can see that it's generally within the acceptable limits. We can also see the trends in the biomass water productivity. Again, we just need to be a little bit careful about looking at the biomass water productivity because without the crop type information, the biomass water productivity will not give you too much of an indicator. But what you can see is a sort of a trend within these 4 irrigation seasons, and suddenly you can see that one irrigation season sort of having a downward trend. Again, this is the type of analytics that you get from the remote sensing, in the sense that remote sensing tells you that there is certain type of trend going on, whether increasing, decreasing trend, but it doesn't tell you why. Maybe it's because there is certain flood event that has happened during that particular time that led to basically destruction of crops in the lower Limpopo, and that basically being reflected in the lower water productivity and lower yield. So at the moment, we are trying to move the system from 100-meter resolution, which is what Yoke mentioned at a national level, to a high resolution of 20 meters. We're also trying to move from a block level applications to a farm level. So there will be a 4 level of applications looking at system level, at the scheme level, sector level, block level, and farm level analytics. And we are also trying to combine with the field-based also in situ information from the stakeholders in terms of estimating the canal efficiencies. And unfortunately, I couldn't show the canal efficiencies because which are sensitive for the stakeholders. So we basically estimate the canal efficiencies with them, and then they submit it to their senior management to get approval before we could show it outside. I conclude my presentation here. Thank you. So if you have any questions, I'm happy to answer. Thank you.
Thank you, Kachi, for this presentation. I think you are providing more details from the first presentation of WAPOR, the complementarity between these 2 presentations. We'll open the floor if you have any questions. Maybe I can start by asking one question. You are using different type of resolutions, but this data used for the 300 for 120 is not the same. And I think the system is based on thermal data. So how do you manage to get information at 20-meter resolution, knowing that there is no satellite providing the images with thermal infrared data at this resolution?
Sure. So at the moment in the tool, we sort of moved from 100-meter resolution to 20-meter resolution because that data was being made available for the Mozambique area. In terms of the 20-meter resolution, the best available resolution directly is the 30-meter Landsat. right? That's the best thermal resolution available. But in terms of this project, Vapor has developed a methodology basically to combine different data sources from Sentinel. So they basically take a land surface temperature from Sentinel, and then they use a machine learning algorithm to basically improve the land surface temperature to a Sentinel temperature, and then use a Sentinel data sets to derive 20-meter data sets. So it's basically a combination of Sentinel-2 data set as well as Landsat data set. That's where you get a 20-meter.
One more time question concerning the validation. When it comes to this level of precision, which kind of processes you are using to validate data, and what is the quality of this validation or the accuracy of data at the end of the process?
So the overall validation activities are handled by IHE Delft. So they look at the project level, trying to identify, they basically try to do the validation for a number of different countries as a project as a whole. But then as a part of a capacity building activities, we collaborate with IHE to do country level validation activities. But having said that, number of these countries don't have the necessary data sets to validate it. So when we go to these countries, most of them, they ask, how do we know that your data set is accurate? And I tell them, we don't know. That's the truth, right? But then I tell them that at the moment, the countries doesn't have any information on countrywide water use. So this is the first set of information that's being made available. So our focus is more on making them comfortable with use of the Earth observation data sets. So and then we do semi-quantitative validation, not full validation as such. So we try to show them semi-quantitative validation in terms of, for example, we calculate the potential ET, and then we have some crop-specific information to calculate actual ET based on the FAO Penman Monteith, and then try to basically compare these two actual ET evapotranspiration methods to see where it fits. And as long as the variations are not so much, then we sort of conclude that it's reasonable, within reasonable amounts. But there are some countries where flux tower estimates are available, for example, in Jordan, where we do full-fledged validation activities. Again, IHE does the full-fledged validation activities. So it purely depends on the countries. In some countries we do, in some countries we just purely stop with the semi-quantitative validation.
Yeah, and in countries, when you have this kind of data available, what is the level of accuracy you are reaching?
Again, to be frank here, it depends on specific crops. For some crops, and that's been the challenge with all the energy balance model, right? For specific crops, the accuracy is up to 85%, right? The actual ET is reasonably accurate. But for some crops, it goes down to 60% of accuracy, right? So I have to also acknowledge that there is huge uncertainty with the use of remote sensing data set, and the uncertainties could come from multiple aspects of it. For example, Vapor uses purely global data sets for the energy balance model. And there was a talk about how the ET is produced. The ET is produced basically using an energy balance model, but then the weather inputs that goes into these data sets are all global reanalysis data sets, right? Which are not specific country level or in-situ data sets, which has got its own uncertainty. The soil parameters that goes into the model is again a global data sets, right? It's not customized for a specific locations, right? There are uncertainties associated with it, right? One of the things I do recommend, again, as I said, that we emphasize on comparing the relative differences. That's what we are trying to do with the irrigation performance. That's why if you look at the out of 11 applications, we have at least 4 or 5 applications of irrigation performance, where beyond the magnitude of that specific variable, what's of interest to the stakeholders, or how one portion of the irrigation scheme performance better than the other performance. So the moment we go into the relative performance, then your magnitude value becomes a little less important. So yeah.
I don't know if you have any questions. Yes.
I'm not sure if you use temperature in your process, in your algorithms, to correct some part of the process.
So there are bias correction methods in terms of using for example, there is bias correction approach implemented by the ELIF. For example, the entire processing chain and the data sets development are implemented by ELIF, the consortium part of a consortium that EOK has developed, right? So they run this standard processing chain, and then they produce these data sets, and then FAO basically coordinates with them to make sure that the data sets are available. And then IHE basically takes care of the capacity building activities, and we basically try to develop this tool. But then temperature is actually a part of the input data set, but I'm not sure. There are bias correction methods implemented in terms of correcting these temperatures or some of the weather variables that goes into these models, but I'm not sure what exactly.
No, it's because it's a very important variable when you want to estimate the actual evapotranspiration. Yeah.
Yeah, but we don't have access to the in-situ data sets, right? Getting in-situ data sets, access to in-situ data sets from meteorological agencies are still very difficult at a country level, right? And it takes time. And for near real-time operating systems, like for example, this one. So for example, every 10th, 1 to 10th, you have one data set, 11 to 20, you have second data set. And so 20 to 30, you have third data set, right? So for example, that's what we call a decade. When one decade ends, within the next 5 days, the data set will be available for that tree, for that particular decade, right? And there is no time, or the time frame is not suitable for us to get access to these data sets and then implement this specific, or tailor this model specific to a particular location or a particular country. And I can tell you, I don't want to name a country, but I tried to access the meteorological data. They quoted me $40,000 for 4 stations. So
Okay.
Thank you.
But maybe
I think the discussion is very interesting. Just allow me, please, because we have two speakers online, and they are from Europe and Africa, and it's too late in these countries. So we can go back to the discussion after the two other presentations we have on the schedule. Thank you.
Sure. Thank you.
We'll rapidly move to the third presentation in this session. And I will call Francesco Volo from the University of Natural Resources and Life Sciences in Austria, who will present the Koala API, a cutting-edge solution for space irrigation scheduling. Francesco, you have the floor.
Yeah, thank you, Mr. Chairman, for facilitating the move to the European time. It's pretty late here. Thank you. I will try to bring another example of how remote sensing data is being used for doing irrigation management. And in particular, we talk about the Koala Enabling Platform, which is a system to produce operationally irrigation advisory information at farm scale. So we primarily work at 10 meter spatial resolution, so it's one pixel size, and the focus is exclusively on the farm, perhaps also on the district scale. I will give also a brief introduction of the different changes that along my career in this area I've been observing. And we can obviously say that there's been improvement in the ways irrigation water is delivered to the fields. So there's been a lot done in that area, but there is also a lot being done in the way agro-meteorological parameters are measured in the fields with the availability of automated weather stations. And we see more and more sensors placed in the field, IoT, but also climatic models that provide, for example, in this case, precipitation data at a quite detailed scale. One of the main problematic we've seen is that there is a mismatch between the scales at which data are provided, for example, from climatic models, from sensors placed in the field, and lately also from satellite observations. And one of the things we see is that data we get, for example, from Sentinel-2, from Landsat-like satellites, they very much represent the variability that we see in the soil. So for example, in this image, we see a Sentinel-2 scene. In green, we have vegetation in brown soil. And on the right-hand side of the screen, we see a soil map of this area. And we see that these spatial patterns are quite well represented in the image. When we look at, for example, rainfall data, they come for this particular region. We're talking about Austria in Europe. They come at 1 kilometer pixel size, which is clearly too coarse, too large to do any management at field scale. On the other hand, farmers also invest in placing sensors in the soil, but those sensors represent very often a variability, an area that is too small, too limited to do management. And the data such as Sentinel come at the right spatial and temporal resolution to really support farmers in irrigation management, irrigation scheduling, understanding of the water requirements of the crop. One of the parameters that at the moment we can best measure with very high confidence from Sentinel-2 like satellites is the leaf area index. And in this slide, in this time series, we see on the top different parcels, in particular in irrigation pivot, how this changes color across the season, and this represents the leaf area index. So it's one of the major parameters used in the estimation of the crop evapotranspiration, in particular based on the FAO PEMA-mounted approach. And today I can confidently say that this parameter can be very well estimated. An example of how Sentinel-2 in combination with reanalysis data or climatic model that provide the classic climatic variables such as solar radiation, temperature, wind speed, the precipitation. In combination with those data and Sentinel, for example, using the PEMA-mounted approach, here we have an estimation of the water balance across the time, so weekly understanding of the ET, the rainfall, and the aggregation of this data for different periods of time to look at irrigation scheduling or water consumption across the season. Koala has been implementing these approaches into a complex system that can manage the different data sets, the different methods, and provide data to the users. So let's have a look at how this works. So everything is implemented in a cloud computing infrastructure where climatic data from models, satellite data from Sentinel, Copernicus, in some occasions also field data are gathered together. So cloud computing can be on Google Earth Engine, can be on one of the European processing services related to the Copernicus data sets, where we also place an orchestrator, so a machine that can handle the data flow, inflow and outflow, but also activate dedicated processing, for example, to do atmospheric correction, to retrieve leaf area index, and to look at value-added products such as evapotranspiration and the aggregation of this value across spatial and temporal scales. The connection then to the users is done via API. I think this is a common technology today, so I probably don't need to go too much into the detail of that. And we imagine in our workflow an intermediate figure, character that takes the data via the API and present this data to final users, such as farmers, irrigation infrastructure, or authorities at district scale. And the data packed together, graphically formatted to be used by these final users. So Koala is not dealing or talking to farmers directly, but via intermediary company is preparing the data and delivering those data. In this presentation, this talk, I'm particularly focusing on the Koala irrigation services, but there's been done more. Particularly, we've been looking at fertilization services as a bit of package of precision agricultural tools. So fertilization has been another big topic, for example, to derive management zone maps or looking at the nitrogen nutrition indices and so on. But again, coming back to us, evapotranspiration is one of the major products. Knowing the precipitation, we can look at the crop water requirements and also provide an indication of the soil canopy water content. And again, all this is done by using Sentinel-2. Because in our experience working across different areas, mainly in Europe, this satellite Sentinel-2 provides the optimal temporal and spatial resolution to address most of the management, the crop types and field size that we have in our regions. Let's have a look at what this orchestrator in the cloud computing infrastructure is doing. So we have some regular processes that happen as new data are coming. So for example, a new Sentinel-2 acquisition is obtained, an atmospheric correction is performed, leaf area index, albedo, fractional vegetation cover is derived, the clouds are masked, and those data are stored into a database, and they remain there until the moment a user is requesting, for example, an irrigation advice or crop water requirement estimation. At this time, an on-the-fly processing is activated, and the previously calculated leaf area index and albedo, for example, are used to, in combination with climatic data, to get ET, so evapotranspiration. And the provision of this data is also done on an adequate temporal scale, for example, by doing a daily time series interpolation and gap filling, so that for every day, even though we don't have Sentinel-2 data on every day, we can provide such an advice. And finally, the information is decoded or simplified into some of the terms commonly used by users, so ET, crop water requirements, and their spatial aggregation. So this division of regular and on-the-fly processing is done to mainly optimize cost of processing and resources use. This is a quick example of how this works. So there is a base address, API Koala, and the number of parameters that users or intermediary providers can adjust. So for example, the coordinates of a point of interest, the date of interest. Let's say we want to have ET for now for a period of 10 days, and we want to have an image returned, and this information is provided. We've been talking in the previous presentation about validation, and being a scientist, this has been at the core of my work, of my interest, and the parameters that we believe are the most realistic to validate across years and spatial scales is leaf area index that we have been extensively validating using the plant canopy analyzer across different crops. And the other variable that we have been also extensively validating with more pain and more work has been the evapotranspiration via the direct comparison with eddy covariance derived ET data across, again, different years and across different crops. There's also been a comparison, this is a particular example for the application of Koala in Australia, with alternative data sets, and this is the TERN, which is actual evapotranspiration derived using thermal data from the Lancet mission. And you can see here a comparison between the ET derived from Koala on a monthly average and the ET derived from TERN on a monthly average. And also in this case, we see a good correlation. The interest for Koala was also to look at providing operational services. And as you have seen, some of this processing happen on the fly, and we don't want users to wait. And therefore, we have also optimized the way all this processing is done. And here you have an example of the response time. So if you submit a request now, you want to get ET calculated, let's say, for last 15 days or longer. And this is an example of calculation across a period of 50 days, and it takes about a second or a bit more than a second to obtain DT for 1 point across about 2 months of time. And on this point, on this aspect, we've put a big effort. So Koala has been also extensively demonstrated with third-party companies that provide services to farmers. That was a bit our approach. We don't go to every and each farmer to demonstrate, but we use these well-established institutions that already have a pool of users, of customers to do the validation. So, for example, we have been talking and integrating with Il-Prophet in Australia. We are currently using Koala to provide data via this Map Timer Explorer in Italy. colleagues in Spain have implemented their own web interface to activate Koala processing via the Koala API. Schedule It is another example of of provider of services in Australia, particularly for scheduling irrigation. And finally, we also been working on creating a plugin for Quantum.js so that you don't need to know complex scripting and your, let's say, Python or R interfaces to derive data, but you can simply use a plugin, and this should simplify the way to obtain data. So what we believe is the innovation and the value. In my opinion, the value is that this data can now be derived, or these products can now be derived very fast, while still maintaining the quality and the accuracy that 10 years ago was derived by having manual expert operators performing, for example, the atmospheric correction, LAI retrieval, and so on. But everything now is automated. And this means that the process is more efficient, the accuracy is maintained, and having such a system at the background means that we can now focus on talking to more users and scale and customize everything, and as a result also save the cost. And the vision is that saving costs, you can go to more users and have this technology adopted on a larger scale and more benefit for everyone. So Koala is a private-public initiative that has been initially funded by the European Commission through research funds. And we are now, the project was concluded in 2023, so last year, and we are now in a phase of searching for additional fundings, additional users, additional demonstration, so that we can continue the operation of such a system and perhaps the further improvements of the services. And therefore, we also provide Koala on a project-by-project basis for scientific use, but also for demonstration if there is a user at the ground that is interested in using it. And you can ask to me directly for an access to it, but you also have online documentation. You will find a reference in this presentation where you can look at the technical documentation or the easy access through some ready-made templates to obtain data for Koala. I thank you very much for the attention and the opportunity, and I'm very happy to take questions now or also online. Thank you.
Thank you, Francesco, for this very interesting presentation, and also thank you for being patient and waiting for us very late in the evening in Vienna. But I think it works that you are sharing this very important project and very promising results from this project. And maybe we can have quickly one question, then we can move to the next one. Yeah. Yes, please.
In your presentation, you mentioned that 10 series data smoothing, that is a very important step to make monthly data or separate this data to daily. Can you say more few words about the principles of this kind of data smoothing or the method? Thank you.
Yes. So climatic data today, they come already on a daily time scale. So this is not a problem anymore from climatic models. While Sentinel-2 Landsat data, because of clouds, because of the revisit time, they come at, it's in the optimal case, at 3 days temporal resolution. And we need to bring those at daily temporal resolution. And we use different algorithms. We use, in this particular case, we use an algorithm called Whittaker, which is a function that helps you to interpolate in between observations. And we have optimized it to run on a data cube so that it can effectively and efficiently provide daily data on a certain time interval. The process is quite complex to go into details, but it has been published and documented on how we do it.
Thank you. Maybe we
Thank you.
can take questions later. Then now we will move to the next speaker in this session, who is Mr. Mohamed Fawzi Smij from the Royal Center for Remote Sensing in Morocco, and he will be sharing with us a project that was developed by the CRTS called Irisat Morocco. Smij, you have the floor.
Thank you, Mr. Chairman.
I assume that you are trying to share your presentation. Okay.
Okay. Yes, thank you, Mr. Chairman. I am pleased to be here with in this conference to share with you some experience.
Maybe you can change your presentation because we have also your notes as well as the.
Okay. Go. It is correct, no?
Yeah, it's okay.
Okay, thank you. Thank you, Mr. President. First of all, I would like to thank the organizer for giving me the opportunity to present our work carried out within the framework of the Irisat Morocco project, whose title is Operational Irrigation Management Based on Remote Sensing. Like many countries in the world, water resources in Morocco is in difficult situation due to climate change. Thus, water saving is the first priority in the new water policy in Morocco. In the agricultural sector, the strategy to safeguard irrigation water involves better management of use of irrigation water, promotion of localized irrigation techniques, and rationalization of groundwater use. In this context, the proposed project Irisat Scope by CRTS was labeled by Space Climate Observatory in 2022 in partnership with French laboratory CESBio and local partners ONVAG, Irrigation Water Distribution Office in Gharb region, and National Institute of Agronomic Research in Kenitra. It is well known that estimating water consumption and needs from satellite image goes through a modeling process. Two families of approaches were used. The first is based on the energy balance, and the second uses the water balance. Our projects use both approaches and tries to find some synergy between them. The projects generate indicators and advices on water consumption and productivity at different spatiotemporal scales. CEBAL approach uses both VIRS data and Landsat data, deals with watershed, irrigation parameters, and plots spatial scale at daily or 8 days frequency. The water balance approach, called SATIR, is more used for plot scale. The energy balance approach in the ERISAT project is divided in three components. The first one uses Sebal model to generate actual evapotranspiration, soil moisture, and biomass from Landsat and VIRS data in conjunction with meteorological and ancillary data. The second module generates indicators on water consumption, water deficit, water productivity, and irrigation advices. The third module concerns dissemination of this product to users. This table resumes generated indicators definition, their production frequency, and end users. There are three groups. The first group focuses on crop water consumption and deficit. The second focuses on crop production and productivity, while the third on soil water reservoir availability. At the same time, the project uses the SATIR platform based on the water balance approach. This platform is the result of the Franco-Moroccan collaboration through the LMI Trema Research Laboratory between CESBio and Qadi Ayyad University of Marrakesh. The goal of this platform is to advise farmers when and how much water to bring for the next 4 days. SATIR platform uses Sentinel-2 data at the plot scales to estimate crop coefficients and the fraction of vegetation cover, calculates reference evapotranspiration using the Penman-Monteith model, and establishes water balance to evaluate crop water requirements. The generated indicator by SATIR platform are actual evapotranspiration, water content at topsoil and root zone reservoirs, and next irrigation date and quantity. As an illustration of the product generated at the scale of the Cebu watershed, it is we show here the actual evapotranspiration at the resolution of 375 meters generated from VIRS data on July 10th, 2020. We show here the same products at the scale of the irrigated perimeter of Gharb at the resolution of 30 meters generated from Landsat data on date of February 11th and April 18th, 2020. Here, the slide shows biomass maps at the same resolution for the same dates. And here we show root zone soil moisture contents maps at the same resolution for the same dates. It is possible to follow the evolution of the generated indicators throughout the whole season. These figures show the monthly average water consumption and biomass evolution for all irrigated crops in Kenitra province. Validation work against flow measurement was carried out on 2 experimental plots of maize and olive trees in Shishawa. The figures illustrate the comparison between estimated and measured evapotranspiration. The root mean squared errors are 0.48 and 0.78 millimeter per day, respectively. To improve the Sebal model, a crop map in the Gharb irrigated area was generated using machine learning technique, using time series of Sentinel-2 images during the 2022 and 2023 season. The main crops are cereals, citrus fruits, beets and sugarcane, greenhouses, fodder crops, and market gardening, etc. To disseminate products, a prototype dissemination platform has been initiated at CERTES. This platform provides access to information on different territorial subdivisions, from the whole water basin down to the individual plots, depending on the user profile, from water basin managers, irrigated perimeter managers, to the farmer. And the example illustrates in the figure shows the farmer's access to the water consumption of his plots and its evolution over time. On the other hand, SysView has produced another prototype of a Satyr dissemination platform designed exclusively for farmers. After registration, the user provides information on plot location, crop type, sowing dates, and irrigation inputs. Throughout the decision, he receives information on water consumption, irrigation advice, and information on the condition of his crop and soil moisture. I will conclude my presentation with the next step. First, creating synergy between CEBAL and Satyr approach by continuing validation works and attempting to combining the models through assimilation mechanism. We begin this activity. The second step is generate products at daily frequency at 10 meters spatial resolution. Third, develop a unique dissemination platform. Fourth, test the system on a sample of farmers before transferring it to startups. And finally, generalize products on different Moroccan watersheds and irrigation perimeters. And this concludes my presentation, and thank you for attention.
Thank you, Mr. Smij, for this presentation and for sharing this, the results and the approach developed by this project in a very specific situation in Morocco, and also underlining the cooperation between two teams trying to combine two different projects on two different approaches to provide information to the end users. Maybe we have time for one or two questions to Mr. Smij, if there is any questions in the room. Please, yeah.
Thank you. The question was more on you were showing different end users, and I was thinking if the platform or the application will have different users. Say I'm an admin, so I'm able to see these variables or this information. I'm a farmer, so I would see only these. Is that something that you have considered as part of the project or as part of new developments?
Yes, thank you for your question. In the platform, in the ERISAT, in the approach used global data, global scale. The platform for dissemination provide different profiles of users. For example, watershed managers have access to all the data for his watershed at large scale. Irrigated managers are access to scales from sectors, blocks, and all the irrigated perimeters, and farmer have access only on his own plots. This is the profile of users. Each profile of users has access to his own data and scales.
Thank you. So the other questions? Well, once again, thank you to our 4 speakers in this session. I think it was an opportunity for us to share different levels of experiences of projects, but I think this is a clear demonstration that satellite data combined by modeling is providing very useful and practical information, and also responding to different kind of needs and of end users' requirements. Also demonstrate that this kind of applications is easily transportable to different regions, to different situations. Viper, for example, project developed by FAO is now available at level country, for example. The project developed by the colleague from the Vienna University shows that there is a high level of value-added services that could be provided by private sector to different companies or to different users. And also the project from Morocco shows that on a national level, there is a possibility to develop a specific project that is tailored to the local needs. So I think from this discussion, we can easily conclude that the high potential of satellite data for irrigation management is demonstrated through these projects. And I think this may be a very promising perspective in the future, and also could be one of the topics that could be developed within the community in Space4Water project to make these solutions, these technologies available and accessible to a large community in the near future. Once again, thank you to the presenters, and also thank you to all participants for this first day. And I know it's a very hard and long day, mainly for person coming from far. But I wish you a nice evening and hope to see you tomorrow and for the second day of our presentation and our conference. Thank you.